Bismillahirrahmanirrahim. Assalamu alaikum, everyone. Welcome to the second session of data structures and algorithms. I'm sorry for getting late on this particular session. So the mode of this session is synchronous. So I'm getting it uploaded in the recorded format. And in case of any confusions or questions, we can always discuss over our WhatsApp group. So in this session, we'll be talking about algorithms, more specifically recursive algorithms. Then we will get to the crux of data structures. We'll study our first formal data structure, which is list abstract data type. We'll discuss its implementation choices, and we'll implement one of its critical implementation choice that is called linked list. And then we'll talk about two more important abstract data types, stack and queue. And then we'll try to go over some other extended abstract data types which are related to the list abstract data type. So let's start with recursive algorithms. So you should be able to record from our from your fundamental Java programming concepts that an algorithm or a function or a method which calls itself is called recursive function. So let's have a look at the first recursive algorithm. So for example, in this particular algorithm, we are naming it as binary search algorithm, but I'm not assuming that you know binary search algorithm beforehand. So what we expect or what we assume over here is that the function or the method which we are defining over here is being passed these four parameters. One is an array of numbers. The other one is the start index of the array. Then we have end index of the array, and then a key is being passed. So key is the element which we are interested in locating inside the array A. So one very important and critical assumption over here in this entire approach is that the given array, which I'm trying to draw over here, is given to us in a sorted format, which means the first element is the smallest one and the last element is the largest one. So let's say we have this array of 1, 2, 3, 4, 5, 6, 7, and 8 locations. We know from our basic concepts of arrays in Java that the first index is indexed as 0. So then it's 1, then we have 2, then we have 3, we have 4, we have 5, we have 6, and the last index is 7, which is size minus 1. So as part of this whole working, what we have been given is that we call this array A. So this has been filled with some numbers. So let's say it has been filled with some numbers, but those numbers have been given to us in a sorted format. So let's say the numbers are 2, 4, 5, 6, 9, 11, 19, and let's say we have another number which is 30. The additional thing which we have been given over here is the key. So key is the kind of data point or data element which we are interested in locating inside this array. So for example, we have been given an element which is, let's say, 21. So our task is to look for 21. So one conventional way, if we don't look at this algorithm, one conventional way of locating 21 is that we write a loop. We start from index 0, and then we keep on moving forward one element by one element. And we compare each element against key. If we succeed to find it, we'll return true. Otherwise, if we fail to find it till end of the array, we'll return false. So that's called linear search algorithm. That's the kind of fundamental search technique which you might have seen or studied or implemented in your basic programming courses. So in this case, we are like trying to do slightly efficient mechanism, and that is that the key is 21. The array has been given to us in the sorted format. So we have these four things. A is the array, key has been given to us. So start and index have been given. So start means that our starting index is 0. This is our start point. The other so this start point has been given to us, and the other endpoint which has been given to us is this last index. So our start index is 0. Our last index is 7. So these two indexes have been given to us. So our algorithm works as follows. We compare the start and n indexes. If start is smaller than or equal to n index, then we compute its midpoint or mid index. So mid is computed as the average of start and the endpoint. So 0 plus 7 over 2 will give us 0 plus 7 is 7 over 2 will give us 3 because we are talking about integer division. 3.5 will be an invalid answer because we are talking about an index. So index have to be an integer. So our midpoint in this case is going to be 3. So in the first iteration, we'll say that our mid is over here, right? So mid is 3. So what we do next is that we compare A of mid. So A of mid is the item which is located over there at that index, that is 6. We compare it against key. If they are same, we are done and we'll return true. If they're not same, there could be two situations. One situation is that this midpoint, A of 3, which is 6, is greater than the key, which is not the case in our example, because 6 is smaller than the key. So we'll get into the else part. And we are now returning something, and that the return thing is not that obvious. That's another function call. So we are calling the same function binary search, and we're passing the same array over here. But this time our start index is mid plus 1, and end index is same as it was previously given to us. Key is same as it was in our previous call. So the only thing which is changing in this call is the start point. So that essentially means that what we do is that we confine our such space to this part of the array, because our mid was index number 3. So mid plus 1 is now the new start. So we are trying to locate elements between this part and between this part. So this is our endpoint, this is our index, this is our start point. So start index is 4, end index is 7. We again find the midpoint. 4 plus 7 is 11. 11 divided by 2 is 5 because we are ignoring the fractional component. So our now new midpoint is going to be index number 5. So what we do is that we land onto this particular index. So when we land onto this particular index, so in our new function call, what we do is that we call this as the new mid. So this is our new mid. And we run the same logic again. A of mid is compared against key. A of mid is 11. 11 is not same as 21. So we get to else if part. A of mid is 11. It's not greater than key. Again, false. So we get again into else part. And we return this as a return thing, we are initiating another call. So we don't have anything available at hand to be returned. Instead, we are initiating another call. So in this new call, what we do is that we are passing the same array, but this time we are passing mid plus 1. So mid plus 1 is now 6. Our endpoint remains same. So we are essentially passing this part of the array. So our start point in this call is going to be 6. Our endpoint is going to be 7. And as we get into this starting logic, so we recompute the midpoint because start is still less than end. So 6 plus 7 is 13. 13 divided by 2 is 6. So our midpoint is 6. We compare it against 21. So now midpoint is 19. That is not greater than 21. So what we do is that we initiate this call once more, but this time our midpoint is going to be 7. Mid plus 1 is going to be 7, and our endpoint is going to be 7. So when we go over here, when we recall this whole function, our start and end both are going to be now 7 and 7. So when we do this thing, we check, we compute the midpoint. That is again going to be 7 plus 7 over 2 is 7. So we compare it against key, we fail, that's not the case. So this time our A of mid is 30, which is greater than 21. So what we do is that we initiate this function call. And if you like carefully look over here at this function call, this is targeting the same array, but now the start point is same as in the previous call, which was 7. And we are now forwarding mid -1, which will be 6. So for this call, which is being labeled in brown, when we call this thing, then our first condition, which was start is less than end, this will become false because start is 7, end is 6. So this condition is false. As this condition is false, so this whole thing which we have been working on was dependent on the truthfulness of this if condition. So as this condition is false, we'll get to the last line of the algorithm. It will return as false because we failed to find 21 over there. Now, if you have observed closely what I have been doing on the screen with different colors, there are many elements which we never compared during our computations. And some of the elements have been compared, some of the elements have been skipped through. And that means that in order to decide whether 21 is there in a sorted array, we can skip some of the elements. So that takes us to the point that what should be the computational complexity? So the computational complexity in terms of big O, in our previous session, which was actually the first session of the course, we talked about big O. So big O is an upper bound on the number of steps which we have to perform. So I had uploaded an additional one-pager handout on complexity. I hope you would have gone through them. If not, then please go through them before we dive little deep into this complexity thing to have a better understanding of what do we mean by big O. So big O is essentially giving us the upper limit on the number of steps. And so the claim over here is that the complexity of this whole algorithm of searching in a sorted array is log of n. So what is log of n? Log of n is essentially this thing. So if you have some number, let's say we have 8. So we divide it over 2. When we divide it over 2, we get 4. We divide 4 over 2 once more, we get 2. So we divide 2 over 2 and we get 1. So we'll keep on this repeated division thing, and the number of steps or the number of division operations which we have performed over here, they are going to represent log of 8 with base 2. As we have performed over here 3 division steps, so log of 8 with base 2 is 3. So logarithm is essentially mathematically opposite to what we do in exponentiation. So for example, if I have been given 2, so to what power of 2 I have to raise it, to what power of 2 I have to raise it to get to 8. Right? So we know that if I have to multiply 2 with itself 3 times, if I replace x with 3, so if x is 3, so 2 raised to power 3 is 8. So that essentially gives us log of 8. So this x or the power is log of 8. In other words, the number of times we keep on dividing 8 over 2 again and again. So the number of division steps which will take us to this base case, which is 1, is going to give us log of 3. In this binary search algorithm, what we have done is that we took an array of size 8. So in the first go, we cut it into half. So when we cut it into half, what we did was that we ignored half the array. We never compared elements over here. We only confined our search space over here. So in the next step, what we did was that we computed the midpoint, and we are ignoring another half of the remaining array. So we keep on doing this whole thing again and again until we are left with only one element. So either that element is of our interest, or we decide that that number is not there. So that's why we are saying that the computational complexity of this algorithm is big O of log of n. So log of n times some constant which we ignore while computing big O is going to give us a very good approximation of the amount of time or the number of steps required to run this algorithm. So what is n? N is essentially size of the input. So we'll be using this variable very frequently in the course to notate size of the input. So this n is size of the input. Okay. Now, what is recursion? Recursion is a programming phenomena where a function calls itself. So we defined a function, and this function is calling itself over here to get the task done, depending on the truthfulness of the conditions. So this is what is the recursive mechanism. So function might be slightly neutral from your as far as your Java background is concerned. So method in Java is same as a function. So function is a relatively generic term, which we'll keep on using again and again as we go along in this whole course. So function essentially means that you have to define a method. Sorry. Okay, let's move forward. So there's a benefit of watching the recorded video because this is not synchronous. So I am unable to pose the questions to you. And obviously you'll be unable to ask me the questions in the live mode. So you can pause the video, you can rewind the video and try to clarify your concepts. Wherever you feel that I might have gone over something quickly. So you can slow it down, you can watch it again and again. But in case of any confusion, please feel free to get back to me so that we can discuss the concerns or issues. Okay, another example of this recursive behavior in mathematics are the Fibonacci numbers. So you might be able to recall from your basic math that Fibonacci numbers are the numbers so starting to Fibonacci numbers are 1 and 1. So Fibonacci number 0 is 1. Fibonacci number 1 is 1. So if I try to write this sequence, this should look like this. First number is 0. The next number is 1. The third number, if n is greater than or equal to 2, which means the Fibonacci number 3 is greater than or equal to 2. So that is sum of the previous two Fibonacci numbers. So sum of the previous two Fibonacci numbers is 0 plus 1. Sorry, let me rewrite them. So if n is, so I'm going to write two things. One is the Fibonacci number itself, which is f of n, which is a function of n. And the second thing is n, which is index of that Fibonacci number. So if we think of the 0th Fibonacci number, which is the starting index, the Fibonacci number is 1. If we think of the first Fibonacci number, that's also 1. If we think of index 2, so now if you look at these two conditions, we are talking about this particular number, which is practically the third Fibonacci number. Fibonacci number 2 means f of 2 is sum of the previous two Fibonacci numbers. So the previous two Fibonacci numbers are known over here as 1 and 1. Right, so this is f of n minus 1, n minus 2, this is f of n minus 1. So we add them and we get 2. So the next Fibonacci number is sum of the previous two Fibonacci numbers, which is 3. Fibonacci number, then and when n is 4, this becomes 5, and then it becomes 8, and this sequence keeps on growing. But the reason we are calling it Fibonacci is that in order to compute f of n, we are calling the same function or same method again twice on two smaller arguments or two smaller parameters. So that's what is recursion. So there could be many ways to compute Fibonacci numbers or particularly to output n Fibonacci number. So this is a function which is being defined as Fibonacci as its name, n is the parameter which is being passed. So we are just translating this mathematical expression in the form of pseudocode. So pseudocode is the code which is not executable, right? So this is a language independent code. It's not particularly a Java or C++ or Python code. So we're just trying to write something which looks like code, and that's the standard way of writing algorithms. And we can conveniently code pseudocodes in the form of any programming language, which is Java in our case. So if n is 0, we return 0. It should be 1. So this is a typo, because we just wrote over there in our math that if n is 0, we say that this is 1. When n is 1, this is 1. So for all other things, which means that we are talking about this last line, that has to be Fibonacci n minus 1, which is a function call, plus Fibonacci n minus 2, which is another function call. So both of these function calls will return their respective Fibonacci numbers. Those will be added up and will be eventually returned to the place where this function would be called from. So now an interesting thing is that if I would strongly urge to compute Fibonacci numbers using this logic on paper, right? So don't use your existing knowledge, just try to replicate this logic or this algorithm, that how good or bad is this algorithm before you move to the next slide. Because on the next slide, we're going to see some magic, which is not a very positive magic. So if we try to estimate the number of operations required to compute Fibonacci numbers, we can compute them using a mathematical mechanism. So Tn is a function on n. T is the amount of time or the number of operations required to perform, number of operations required to be performed in order to compute nth Fibonacci number. So if n is 0, we are saying the number of steps are 2, because we are performing one if statement, and another one is the return statement. When n is 1, we perform the first if statement, which was false. Then we check the second if statement, and then we're returning something. So our exact number of steps are 3. But for the third one, we have already done 2 steps in failing the first 2 if statements, plus the third one is the return statement. And so those 3 steps have to be added in the amount of time which will be required for Tn minus 1 and Tn minus 2. So Tn minus 1 is the amount of time to compute f of n minus 1. And Tn minus 2 is the amount of time which is required to compute n minus 2. So when I say the time required to compute f of n minus 1, I don't mean the physical time of clock. By that time, I mean the number of steps or number of operations required to get that task done. We are trying to approximate the number of steps of that particular operation. So if like I'm not expecting you to solve this thing like all at once, but if you have taken a discrete math course, which some of you shared that you had taken it in your previous semester, so you can use your basic knowledge of recurrences and try to solve this recurrence. And even if you don't have the knowledge, then just believe me for a while over here, that if you solve that recurrence using a method, which we are not really very particular about, that how to solve that whole thing, that turns out to be that time is going to be greater than 2 raised power something. And if you look at the something which is getting in the power is a function of n. So if you recall your basic math, so if there is a constant in the base or there is some base, if we have this n variable in the exponent, that means that we are going to represent something which is very closely related to an exponential function. And the interesting thing which I wanted to show you over here is that for n is equal to 300, which means that we are trying to compute 300th Fibonacci number or F300, that will take us 2 raised power 150 operations. If you just plug in this n300 over here in this expression here, so that's going to take us 2 raised power 150 operations. So what does that mean in physical terms? So if you have a supercomputer which is very fast, like if it has a frequency of 64 terahertz, then it will need 2 raised power 104 seconds to compute this whole thing. And if we convert those seconds to hours and years, that turns out to be 10 raised power 23 years, which means so just imagine 10 raised power 23 years. 10 raised to the power 2 is 100 years. So we are trying to put 23 zeros with 1, and that many years are required to compute f of 300, which is not a like very large Fibonacci number, if you go with that logic, which we've just seen in our previous slide. Okay. Now, why are we looking at this thing? One important realization which we need to have over here is that if our algorithm is not efficient, then our physical hardware is not going to be very helpful. That is going to lead us to a mess, and we need to be very careful about it. We should try to optimize all those kind of algorithms if we can. So if you look at this red expressions, if I try to summarize this expression, we can write in the form of big O that this whole thing is big O of 2 raised power n. So why we are writing it as 2 raised power n? Because in terms of big O, we just slash this constant, and this gives us a very good approximation that actually we're talking about something which is exponential in time, which is a very bad type complexity. For any reasonably large n, it will take a lot of time. Okay, so this is the a summary of different big O functions. So if we have something which is big O of log of n, as we saw in binary search, that is somewhere here on the bottom in the green region. Big O of 1 is the special notation which is used to notate constant complexity. If there is an algorithm which needs constant number of steps and does not depend on size of the input, which is small n. So then we notate that constant complexity as big O of 1. For example, if you have an array as the input, which contains, let's say, 10 elements, and your task is just to return the first element, so you can return it in constant number of steps. You don't need to scan the whole array. Now, if I change n in that case, if I have an array which is of much bigger size, let's say 1 million size, and task is same, that we have to return the first element. So we can still get the same logic, and we can return the first element, which is located at index 0. So our time is constant. So in that case, we'll be using this notation of big O1. So big O1 is a notation which is an ideal thing, that its complexity does not depend on the size of the input. So it does not change with change in n. So that's an ideal situation. And we use this big O1 as a standard notation to represent constant amount of time or constant number of steps or operations required to get that thing done. So if something, it takes big O n, so it's like in the yellow region, visually over here, which means that this is not as good as green thing, but still it's okay. Then n multiplied by log n is a bigger number than big O of n, but n square or 2 raised to power n or n factorial, they're going to be like horrible numbers if we try to imagine them in terms of large n. So just try to substitute a bigger value of n, and this number is going to blow up, as we have seen in the case of Fibonacci numbers on our previous slide, that when n was 300, then this 2 raised to power n actually blew up. So that kind of logic can be a disaster for a computer program, because it will be taking unimaginably huge amount of time. Okay, now we are getting to our data structures part. This was a sort of like programming recap in terms of recursion. I would strongly urge you to write recursive functions or recursive methods in Java to implement binary search, to implement Fibonacci numbers, or you can come up with many other things like factorial, or you can write program to compute greatest common divisor of 2 integers. Try to write recursive code so that you become really comfortable with recursion. Recursion is one of the important programming cornerstones. So as a computer science or computer engineering student, we must be very comfortable with recursion in terms of our coding skills. Okay, abstract data types, we will keep on abbreviating them as ADTs. So a conceptual data type is an abstract data type which has a well-defined behavior. By behavior, we mean that what kind of operations can be performed on the objects of the data type. For example, we'll see certain things like stack, queue, priority queue, or friend on Facebook. So just imagine that how people would have implemented Facebook. So one person is one object in that entire ecosystem of Facebook, so that you can imagine one person or one user as an object. But that object has a lot of associated behavior. Like, so if there is a friend, you can add a friend, you can remove a friend, you can search a friend, you can send a message to the friend. And so all those things are the associated behaviors which primarily define that conceptual data type whom we are terming as friend on Facebook. Now, the question arises that if we have figured out that what should be the behavior of a uh, particular abstract data type or conceptual data type, how to implement that abstract data type. So for that purpose, we need to go for some concrete backend implementation. And that actually takes us to what we call data structure. So when we implement that abstract data type, that implementation is called data structure. So our first abstract data type is called list. And this list has the same meanings as those of in our real life. So we have like a list of shopping items. We might be having a list of items in our online cart, might be a list of tasks which we need to do in a particular day. It could be list of courses which you are taking in this semester. For me, it's a list of students who are taking my course. So we can imagine a list of different things, and that's an ordered collection of items. So a list of grad schools I need to target next year. So what we do is that we need to characterize types of items in each list. So if we are talking about a shopping list, then the items will be having a different nature. If you're talking about the kind of task which I need to do as part of my today's calendar, those could be like different kinds of items. So from the object-oriented programming perspective, an item means that we have to create a class for that item. So it could be an array of objects, it could be a collection of objects, but essentially each item is an object. And because like we have now Java background, so we know that what do we mean by an object. So object is a real world thing. It's like it has a like conceptual or abstract meanings. And once we try to code them, we need to create a class, and then that class needs to have some objects in terms of our implementation. The question is that how to implement the list abstract data type. So in data structures or in programming or in Java or in many other languages, when we think of concrete implementations, we have two major choices. There could be many choices, but there are two like important choices which we are going to discuss. So first choice is called array, that we use a backend array in Java to implement a list. The other choice is linked list. Array is something which I'm sure you are familiar with from your programming experience of Java, and we'll be having a very quick recap of that thing. But linked list is the kind of thing which you might not have encountered so far, or I'm not sure, but some of you might have seen it before. But we'll be going over this linked list stuff in little detail in terms of Java implementation. Okay, now, if you look, if let's try to have a like subjective or abstract level comparison between array and linked list. So if we create an array in a program, so array is a contiguous memory allocation. Array is a collection of items, so all items are placed next to each other in the memory. In terms of linked list, it's a non-contiguous memory allocation, which means that all those objects can be scattered anywhere in the memory. Array usually has a fixed size, whereas linked list is a dynamic size data structure. So in terms of array, all items are allocated memory space all at once when we create the array. But in terms of linked list, those items are given memory item by item as we need. So we know from our array background that array is an indexed data structure, which means that indexing starts from 0. The first element is located at index number 0, then 1, 2, 3, up till size -1. But in terms of a linked list, there is no indexing mechanism, and we need to have an alternate way of accessing things. And that's what we'll see in a while. So if you look at the figure on top, that's an array, right? It has 8 elements. The first element is index 0, last is 7, which is size -1. But if you look at the other data structure, which means, so this data structure, one box, by box, I mean this component. Like if you look over here, so this is one item. So this bold arrow notates that this is start of the linked list. So this is start of the linked list. And we might be having some item over here. And then the second compartment of that bigger object needs to have a mechanism to know memory address of the next element. So when you get to the next element, that stores some element. And again, second compartment over here is responsible to hold memory address of some other item over here. So it knows that where is, let's say, 40. And this goes on. So when we reach to the last element, it stores its data over here. And it's then this address thing points to something which we call null. So by null, we mean that this is the end of the linked list. Now, if you look over here on this visualization, so all these items are essentially scattered somewhere in the memory. So this item could be anywhere in the memory. This could be anywhere in the memory. And what we know is that we have to have some explicit mechanism to remember address of this particular box, this particular object in our in a memory, right? So the first object knows where is the second element in the memory. Second object knows where is the third element in the memory, and so on. But in the case of array, because all those locations are contiguous to each other, so this addressing mechanism is being implemented implicitly in the whole implementation as an array. Now, if you look at the array implementation, that's how it should look like, that we need to create a class. We call it list. So list is the abstract data type. So we are implementing that abstract data type list using an array as the concrete implementation. So in terms of list, before you look at this code, just like imagine that what kind of things should be there in the list. So for example, in this part of the code, what we're doing is that our list can contain at max 10 integers. So we create an array of size 10. So it's a fixed thing. So we need to know that how many elements are fixed. We call it size. We have a constructor to initialize things. And then we need to have some methods which can help us to insert different items onto a particular location in the array. And we might be having like some removal mechanism from a particular index. We can have another function which can just return us that how many elements are filled in the array, and so on. So once we fill these methods, that starts looking like a list. And in our main function or main method, what we do is that we create object of the class list, and that list will contain the whole thing of 10 elements. So 10 empty boxes will be there. We can start filling them using this add element thing, or we can manipulate them using any other alternate thing. So I hope it makes sense. If not, then please feel free to get back to me. Now, the question is that how good or bad would be the different methods if we have to implement a list using array? So what will be the cost of adding something at the start? So let's try to create an array of some hypothetical size. So let's say we have an array which has some elements over here. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is 0, this is 1, this is 2, 3, 4, 5, 6, 7, and then this is 8. There are total 9 elements over here, starting from index 0 to index 1. So this slide is your task. add at start. If I have to add some elements, so just to keep your life a little easier, you can assume that some elements have already been added, right? So let's say 5, 7, 2 are there. So n is over here the total size of the array, right? So total number of elements which we have in the input. So if I have to add an element at start, what should I do? Just pause the video over here. Ask yourself that what will you do to add an element at the start? And at the same time, think of the logic, but at the same time, try to come up with this estimation of computational cost, that in terms of big O, how much amount of time will be required to do this whole thing. So if you had paused the video, you might have come across thing that if I have to add 4 at start, I need to move all these elements first, one step towards right. 2 needs to move here, 7 needs to move in place of 2, 5 needs to move in place of 7, and then we can add some new element over here. And if that is reasonably filled with the large number of elements, then we'll have to shift all those elements. So in that case, our big O of adding at start will be, this has to be big O of n, because we might be encountering n number of shift operations. If you think of adding an element at the end, what do we need to do? We don't need to have any shift operation. We just need to remember that what is the current size, how many elements have been filled, and we just drop our new element over there. Which means that irrespective of size of the array, we can get things done conveniently in big O1, which represents the constant number of steps. Okay, now, what about adding at a given index? If you have to add an element at a given index, what will be the cost in terms of big O? So that index, in the worst case, that index could be 0. So if the index is 0, then we need to shift all those elements. So in terms of big O, we should always represent our big O complexity in terms of the worst case. So in the worst case, this has to be n because it might be involving a lot of shift operations. If you have to remove an element from start, what do we need to do? So if I have to get rid of 4, I need to bring all the previous elements back to their original positions. That means then another like n shift operations are required over here in order to remove something from the start, because if you don't shift them, then the whole like overall pool of algorithms will become more complicated and will not make much sense. So what about removing from end? So removing from end is again like convenient because we can remove things from the end. Last element which will be the only one which will be having which will be impacted. So our cost is going to be big O1. Okay, how about removing from a given index? Again, this given index could be in the worst case could be 0. If it's 0, then we need to perform a lot of shift operations. And in that case, it has to be big O of n. So I hope we are okay. The next slide actually contains these solutions in a decent font. So you can have a look over here, try to convince yourself that why these complexities are of this much mathematical expression. You can, I would strongly suggest to do some paperwork over here, right? Try to create a like hypothetical array, try to add elements, remove elements, and see that how these operations are taking that much amount of time. So this is what is one implementation choice to implement a list. So second implementation choice is a linked list. So linked list is something which is new for us. We might be spending some time on understanding the linked list, but if you look over here, we have two classes. So the first class is essentially defining a node. There are two parts which we are going to put over here in the node. So one node will be looking like this. The first part will contain our data. So we are assuming that our data is integer. So we'll be creating one integer. But if our data is like a lot of other stuff, we can create any other like we might be having an object over here, or what might be having many attributes over here. But if so, that's what is int data. And if you look at the second part, which is node next, so that is a reference. So its type is node, which means that this next thing can hold address of another node. So If there is another node, its address will be held by this next thing. So these two things are very important. Why we need to have this next? If you are able to recall the previous visualization, we saw that one node needs to know memory address of the other node so that that chain gets that chain remains intact and that whole linked list gets created. Then we have two constructors over here. The first constructor is an empty constructor. It does not have any parameters, which means that you can set data to 0 and next to null. And the second constructor is that if you have some data, you can pass it over here and you can set next as null. So in a while, I'll show you this code in the live mode. We'll implement this linked list in the next few minutes. So the first class is essentially defining the building block of the linked list. So one node is being defined by this first class, which is called node. Then we create another class, which is called linked list. So now linked list is a chain of different nodes. So the first node is of type node, and we call it head. So in the linked list constructor, we initialize this head to point to null, which means that this is an empty linked list. And then we add different methods within this class. One is added start. So if you look at the names of these methods, these are very similar to the ones which we've just seen in terms of the array. So there was an alternate implementation of implementing list abstract data type. This is another implementation of implementing the list ADT. But the interesting thing is that if I try to like visualize this chain, so this is, let's say, the head node. So the first node is here. So that is called head, or head knows address of this node. Then this points to another node. This points to another node. So you can imagine that we have like a lot of nodes in the linked list. And then we have this last node, and it points to null, which means this is the end of the linked list. So this does not point to anything. Now, just imagine that if I have to add a new node at the start, I'm talking about this first method. So what should I do? I know where is this first node. And so what we do is that we're using the first class node, we use its constructor, we create a new node. So this is an isolated node. Because we have to add it at start, we just need to connect this node with the linked list so that this red node becomes the first node and its next becomes the current start. So it starts pointing over here and we ask the head to point over here. And these two simple assignments make this whole red thing embedded in the linked list at the start. So if you have captured what I did with the red arrows, so I actually did two assignment operations, which means that I did the constant number of operations irrespective of how long the chain is, how long the linked list is. So that gives us a clue that we can get this whole thing done in Big-O-1, unlike the arrays. If you are able to recall the arrays from our previous slides, we just said that adding an element at the start using an array needs a lot of shift operations. So there is no concept of shift in linked list because all those addresses can be beautifully maintained and connected, reconnected, and adjusted, and we can optimize a lot of stuff. Now, if you think of add at end, that is critical to understand. And the reason it's critical is that this is very different than an array. So we know that we were able to access any index using the array, but linked list does not have an indexing mechanism. What we know is that where is the start node that is being pointed by head. So if I have to get over here, if I have to create a new node, this blue one, if I want to make it as the last node, so next of this node should be null. And this actual last node should start pointing over here. If it starts pointing over here, then this thing gets overridden. But how can I reach to this node to change it? So for that purpose, I need to start from head. I need to walk through the whole chain step by step, and then I reach over here. And that's the only way to scan the whole list. So that means that adding a node at end will be taking like a lot of more steps if I have only head and I keep on walking over the list, and that takes us to big O of n complexity. So its complexity in this case, in this kind of implementation, is going to be big O of n. But some people have like overcome this issue in a smarter way. And that smarter way is that like unlike this thing, they maintain another attribute over here, another data member over here. They call it node tail. So they create another pointer, another reference over here, which keeps on pointing to the tail or last node of the linked list. So if you know the tail, then you can directly access this thing using that tail thing, because the tail will be pointing to this last one. So in that case, this big O n will be dropped down to big O of 1 if we have this tail reference with us. But if you don't have the tail reference, then we'll have to scan the whole linked list. Again, because we are doing it in a asynchronous mode, so please like pause, rewind, and spend time on each of the discussions which we are going, which we are doing over here. Now, the same task, same exercise which we did for arrays. Ask yourself that what will be the cost of each of those operations, solve them on your own, and then we are going to discuss those solutions quickly. So pause the video over here before you move forward. So if you pause the video and you are back, so you might have seen that adding at start is a quick thing. Adding at end is also a quick thing if we have the tail pointer, right? So over here, the assumption is that we know the tail. If we know the tail, then adding at n is big O 1. But if you don't have the tail, then it will be big O of n, and we'll have to scan the whole list. And adding at a given position could be big O n, because we might have to scan almost n elements in a list. If, for example, if you have to put something at the second last position or third last position and so on. So removing from start is convenient because we just need to manipulate. We need to do some reassignments with the head. And removing from n is going to be big O of n, irrespective of you have access to tail or you don't have access to tail. You will have to scan the whole list, and removing from a given position will also take you to big O of n. Okay, now there are like some problems which I'm going to share with you. I would strongly suggest that do those problems. So write a complete program to implement the list ADT using an array. Once done, write a complete program to implement the list ADT using a linked list. This second problem is extremely important. We are going to solve it over here. I would strongly urge you to understand that, but don't copy it. You can copy it if there is no like alternate, but in order to really make sure that you understand things, I would strongly encourage each of you to do that thing on your own. Extend your above programs to sort the linked list. If you have sort the whole linked list, how can you like extend your program number 2? Then there are two more ADTs which we would like to go over. One is stack ADT. The third one, the last one is queue ADT. But before I get to stack ADT, so I'm taking a pause over here. And what we are going to do is that let's get to the implementation part. So I'm going to take you to the this Eclipse screen, and let's try to implement what we have understood till this moment. So we are creating a class node. So so I'm actually implementing the linked list. So node contained two things. One is that it will be having a data member, which is of type integer. And the other thing is that it will be having a reference of type node, whom we are terming as next. So then we create a constructor. So this is an 0 parameter or 0 argument constructor. So if you don't know data, then we can initialize it to 0, and we can make next as null. So null is the keyword which will help us to do some manipulation later on. Or we can overload the constructor. We can have another constructor which where we know the data, and for that purpose we assign D to data and we keep next as null. So these either of those two constructor choices will help us to create a new object of the class node. So whenever we have to add a node, we'll need this kind of we will need an object of the class node. So what kind of operations we can perform on node? There could be many. So I'm skipping them for a while. So let's get to the other class, which is a bigger class. So that's what we call linked list class. And in that class, what we do is that we create a reference of type node. We call it head. So this head is now going to point to the starting node of the linked list, which means that head is the controlling point of the linked list. Head knows what is the linked list. If we somehow lose control over head, we are going to lose the entire linked list, because that whole chain of objects of type node are going to be chained together through this one. So in the linked list constructor, we initialize head as null. What does that mean? That means that if we create a public class, let me call it test. So public static void main. So in main, what I'm going to do is that I'm going to create an object of linked list class. So let me call it I call it my list. So this is the name of the objects, and we instantiate it using this constructor linked list. So the new object of type linked list will be created. Its name is my list. And that my list will be containing only one attribute whose name is head, but that will be null because that's what we have done in the constructor. So what kind of stuff we can do with this whole thing? What kind of operations we can perform over here? So if you are able to recall, so I'm going to implement some of the operations, and I would strongly urge you to complete that implementation. So let's say we create add at start operation. We pass it a node X, and we expect that this method add at start will be putting this new node X at the start of the linked list. What does that mean? That X is the node which is being passed to us. So the list is already there, and that is being controlled by head. So head is pointing to the first node of the linked list. That could be null if it's an empty list. But wherever head is pointing to, now we want X to point to that place. So what we do is that we write here X dot next has to become whatever is head pointing to. So head is a reference of type node. Next is also a reference of type node, so they are type compatible. X dot next is assigned head, which means that address which is being held with head should be now given to next, and then X should become the new head. So X becomes the new head, and that's it. So these two lines actually help us to add this new node X at the start. Now how to get it done in main? So we have already created the object. Its name is my list. So what we do is my list dot add node at start. So there could be many ways to pass the node over here. So we can pass a new node, anonymous node, without giving it a name. We pass it some value. Let's say we pass it 10. So 10 goes to the constructor node. So if you look over here on line 10, 10 will go in D. That will be set as data. Its next will be null. So that object which we are passing over here will be referred as X in this call, and that will be containing 10. And that has to become the first object. If we call the same function once more, if we call the same method once more, and we, let's say this time add 20, and we add it once more, we call it 30. So 3 nodes should be added at the start. So take a pause, try to figure out yourself that who will be the first node after running this, after calling this function 3 times. So far we don't know. So what we do is that we need to write another method to verify our stuff, the kind of stuff which we've done so far, that is it really working. So what we do is that we write here void display in the linked list class. So this function is critical to understand. This function is supposed to scan the whole linked list and display data of each node. So what we know so far is that head is the start point. We don't know what else is in the linked list. So what we do is that we create a temporary reference. We call it current. We initialize it with head, and then we run a loop. Loop is that while current. So current is a reference. While current is not equal to null, that means that current is pointing to a valid object, because current is not null. So it means the current is now holding address of some object. So if it knows address of some object, it should be having data. So what we do is that we ask it to print data, and that data could be current dot data. And then we can append some space over here just for the sake of clarity. And after this line, what we do is that once the data of that object which was being pointed to current has been displayed, we move current to the next object. So we ask it that change current to current dot next. It checks the loop again. If it's not null, it will pick the data of the next object. We'll move the current one step forward. We'll check the loop again. As it reaches end of the linked list, this while condition will become false and it will get out of the loop. So we can write here something system dot out dot print, somewhat like \n kind of thing, just to keep things in a neater way, that current content of the linked list is as follows. So now what we can do is that we can do a quick verification from here. We write my list dot display. We call this function, and if we run this, we can see that over here in the output window that current content of the linked list is 30, 20, 10. So 30 is the last one which was added at start. 10 was the first head, then 20 was the next head. So 10 was moved to the item number 2. When 30 was inserted, 10 moved to item number 3, 20 became number 2, and 30 became number 1. So that's what is being presented over here. So I would strongly urge to, using this display logic, try to implement the function on your own, that how to add an element at the end. So what I'm going to do over here is that I'm going to write another function, void remove from start, and does not need any parameters. We just need to remove the first element. So first element is being pointed by head. So what we want is that the element head should start pointing to head dot next, right? And if head dot next, so if head is already null, then this will be a valid thing, invalid thing. So what we ask is that if head is not equal to null, that means that it's pointing to an object. So then it should start pointing to the next element, which means that the first element will be ignored in that case. And what we can do is that we can call my list dot remove from start, and we can verify that whether my list dot display is displaying things in a decent way. We run it. Now there are two outputs. So 30 was the element at the start that has been removed in the next line. So you can see in the output in the second line. So if I call this function once more and then display the contents, So we can analyze it that if it has been another element has been removed, then 20 is gone and 10 is left. And if we do the same thing once more, so now the list becomes empty because we've called that remove from start 3 times and list is there's no more element. So it does not display anything. So this is the kind of stuff which I hope you were with me and you captured the essence of what we are trying to do over here. Uh, there are like 2 more ADTs which I would like to go over and then we'll stop. So stack abstract data type and queue abstract data type are also type of list types of some specific types of list ADT. So let's go over stack ADT first. So stack is the kind of, if we like think of a bucket, we place some books in the bucket. So if bucket has walls around it, then bottom is also packed. So there is only one point in the bucket where we can insert or remove elements from, and that's the top. So that's what we call this a last in first out protocol, which means the element which was inserted at the end has to be removed first because that is on the top of that stack. So 2 terminologies are used over here in the context of stack. Adding an element is called push operation. Removing an element is called pop operation. So let's start with an empty stack of size 5. We try to push A, B, C, then we pop, we push D. And now you can pause the video over here, take a piece of paper and pen, try to draw a stack that how, if we run these 5 or 6 steps in the sequence, then how the stack should be looking like after each of the operations. So pause the video and try to do it on your own. So if you pause the video, you might have seen that it looks like this. So first once we push A, stack is like this. B will go on top of A, C will go on top of B. When we pop, C has to go first because the element on the top will go first. B cannot be removed before C. And then we push D, so D goes on top of B. So now if you think of all these operations, push and pop operations, we can use an array to implement the stack, or we can use a linked list to implement a stack. But we'll have to limit our operations. We cannot randomly or arbitrarily add or remove elements to or from the stack. So that order has to be maintained, which says that the element which was added at end has to be removed first. So which one is better? Array is a better implementation choice or linked list? Ask yourself, try to analyze the complexities. So if we try to use an array, so what will be the cost of pushing an element in an array? Because we're using array as an underlying data structure to implement a stack ADT. What will be the cost of the pop operation? Because we're using array as the underlying data structure for implementing stack ADT. And same is the case of linked list thing. So again, pause the video, ask yourself, fill in these 4 items in the tables, and the next slide will show you the solutions. So if you pause the video, sorry, so the next slide did not show the solution, but I'm going to show you the solutions. So the push operation, we're talking about array, right? So we have two. So whatever we have a choice. If this is the array, so if we use this site for, if you say 0, this is 1, this is 2. So we are essentially adding at n and removing from n. So both of the items can be performed, both of the operations can be performed in big O1 and big O1. Sorry for my poor handwriting. In terms of linked list, again, we know that if you use the end, which is at the start, so both of the choices can be done in big O1 and big O1. So stack is like can be implemented in a very decent way, irrespective of how big it is, using arrays as well as linked lists. Because both of the operations, push and pop, have to be performed on the same end. Versus another ADT that's called Q, first in, first out protocol, which means the element which was added first will be removed first. So adding an element in a queue is called an queue operation. Removing an element from the queue is called dequeue operation. So start with an empty queue of size 5. Perform these 3 operations. NQA, which means add an element to the queue, add element B to the queue, then add element C in the queue, follow the sequence, then DQ, then NQD, and show the queue after each those steps. Pause the video, try to do on your own on the paper, and then verify the answers. So when we NQ A goes here. When we NQ B, B goes there after A, C goes after B. So when we say we are performing this DQ operations, that means that the element which was added first, that has to go out. So this side is being used for adding elements. The other side has to be used for removing elements, because that side contains the elements which were added first, and we have to maintain that order of first in, first out protocol. So unlike stack, 2 different ends of the data structure are going to be used for these 2 operations. So same way, we have the choice of implementation. 2 choices are with us. We can implement a queue using an array or linked list. You have to analyze which one is better. Now, if we, again, like take a pause over here, fill in this question sheet on your own. And after the pause, we can discuss it. So if you think of an array, I have to add an element on one end, remove an element from the other end. So it depends on your choice. If I use start as the point for NQ, then that we know that is the costly point. So we will be spending big O of n due to those shift operations in NQ, but we can remove elements quite conveniently from the other end in the array. Now, from the linked list perspective, if we have the tail, in the example which we like partially implemented a while ago in Java, we did not have the tail, but you can always use tail to optimize the cost. So if we know the tail, then we use the tail for NQ operation, and our addition operation will always take big O1. And if we use the head of the linked list to remove elements, we also know that that can be done in big O1. Now, unlike array, this linked list supports both of the queue operations to be done in big O1, which means constant number of steps. And this is going to be very effective if you have a very large queue. If you have a large number of data items which need to be stored in the data structure, then linked list is going to be an attractive choice to implement a queue versus an array, because in the array, at least one operation has to go in big O n, which is going to be an expensive one relatively. So like we are almost done for today's session or for this week's session. So in our next class, we'll be like talking about some extensions of linked lists. We call them doubly linked lists, double-ended queues, circular queues, and like if you have time, if you have interest, if you want to explore them on your own, you can explore them, and that will help us to speed up things in the next session, which will be a live session, inshallah, on Tuesday. But if you have like, if you you should be getting to those topics only if you have implemented a linked list on your own. Okay. So once you're done with this thing, I would strongly suggest that do these first 4 steps by Tuesday. Implement stack ADT, queue ADT, once you have implemented arrays and linked lists as the list. So you'll be using those pieces of code to just modify them and implement them as stack and queue ADTs. For problem number 5, 6, 7, those are the optional ones for this week. If you get time and if you have your own interest to move forward, you can get to doubly linked list, double-ended queue, and circular queue. Otherwise, we'll be doing them at the start of our next session, and then we'll be concluding this list stuff. But I would strongly suggest and reiterate over here that please make sure that you implement please make sure that you implement this linked list on your own. It's an extremely important concept in data structures. It's an extremely important implementation pillar. One of the very common thing which people ask in interviews and admission tests. So I would strongly suggest I'm available on WhatsApp. Please feel free to let me know if you face any difficulty. But spending time in coding with linked list will pay off later on. And if we somehow fail to have a good grasp over linked list, that will cause problems in the coming days. So it's strongly suggested that please try to spend more time, have a very good, strong hands-on on this thing. It will definitely help us in building more complicated data structures. Thank you very much.